4.5. I am. Thank you. Way to go, Bailey. You are on it. I love it.
I'll watch it on YouTube.
Okay.
See ya.
Bye.
See ya.
He's lying. He's not gonna watch me on YouTube.
Okay, so section 4.5. Tangent line approximation.
Isn't this what we did like the first week?
We wrote equations of tangent lines, but we've never used them to
Find the equation.
approximate like other values. Okay. All right. So remember that what we're studying in chapter 4 are applications of derivatives. Okay, applications of derivatives. We've just completed our first big application, which is being able to sketch graphs from all the information you can gather from your first and second derivative. Okay, so this second application we're going to talk about is tangent line approximation. You've been writing equations of tangent lines since about the first week of school. Okay, but now what we're going to do is we're going to take those tangent lines, we're going to use them to approximate. Today's lesson seems a little silly with the tangent line approximation because it's like, well, I have a calculator. Why wouldn't I just find the value with the calculator? And I get that. But we have to start somewhere because ultimately what we're going to do is piece together all of these little tangent lines to come up with a function, okay? To come up with a graph of a function that we can't create. Okay, like you can't write an equation for this function, but you can put together all these little tangent lines and create one. Okay, so that's the purpose behind this. There's more to come here. This in and of itself is a little, Okay, so here we go. And it's also called linearization. Your textbook calls it linearization. Instead of saying write an equation of a tangent line, it will say write the linearization of f of x. So don't let that term freak you out, okay? If a function is differentiable at x equals a, if a function is differentiable at x equals a, what does that mean? Anyway, you can find the derivative there, good. Then the equation of the tangent line at x equals a can be used to approximate values of f near A. X equals A is called the center of the approximation. Okay, if a function is differentiable at x equals a, then the equation of the tangent line at x equals a can be used to approximate values of f near a. X equals a is called the center of the approximation. So, here's what I'm talking about. Okay, if you have a function and you write this equation of the tangent line that at x equals a, this tangent line can be used to estimate values on the original function as long as I stay really close to the what?
A.
The point of tangency, right? Like I'm not going to use this tangent line to approximate a y value on the function way over here, right? Because I'm very far away from the point of tangency. Okay, so again, sometimes we get these graphs of things and there are no equations to describe what's happening. Okay, but I can find a point and I can find a slope at a point, and then I can use that tangent line to approximate a y value on that function that I don't know its equation. Okay? So we're going to start with an example, again, where I know you're going to be like, well, if I have a calculator, why would I do that? We're just learning the rules so we can play the game. Okay? Find the tangent line to f of x equals cosine x at x equals pi halves. You use it to approximate cosine of 1.75 and determine the accuracy of your approximation. Okay, so in other words, I've got this cosine curve, right? I'm going to write an equation of the line tangent to this cosine curve at x equals pi halves. And then I'm going to use that tangent line to approximate cosine of 1.75. In other words, take 1.75 and substitute it in where in your tangent line? For x, right? For x. And that's all I'm going to do, and then I'm going to compare them. Okay, so let's write the equation of the tangent line. What two things must you have? Point and the slope at that point. Do I have a point?
Yes.
Well, sort of. I have the x value of that point, right? So I can find it by doing f of pi halves. And f of pi halves means cosine of pi halves, which is 0. So the point is pi halves 0. And the next thing I need, you told me, is the slope at that point. So I need the derivative. So what is the derivative of f of x? Negative sine x. And I need that when x is pi halves, right? And that is negative 1. So the equation of your tangent line is
y equals negative x minus pi.
right? Which you can make y equals negative x plus pi halves, right? Okay, and just so it doesn't freak you out, like a linearization, if you saw this in the textbook, it might look like this. L of x equals negative x plus pi halves. If they ask you for a linearization, sometimes they will make that say capital L of x. Okay. Now it says use this tangent line that we just came up with to approximate cosine of 1.75. So what do I need to find? I need y of 1.75, right? I need to plug 1.75 in for that equation. So that means negative 1.75 plus pi halves. Somebody have a calculator out?
You said you couldn't use a calculator.
No, what I was saying was it seems weird that you would do this problem because,
Calculus rep, we need your.
yeah. You got it for me, Ryan?
Negative
0.179?
Yeah.
Okay. Okay, so this is my tangent line approximation, right? Of cosine of 1.75. You have your calculator out. Find cosine of 1.75 for me. Okay, was my approximation pretty good? I don't know. It depends on how accurate you need to be for what you're doing, right? So if you're building a bridge with an arch in it and you need the arch not to fall, I don't know if that's good enough. Okay, so you've got some error that you'll have to work within. All right, but it said determine the accuracy of your approximation. There's
Yeah, if you're
a
building a bridge, I think you'd be using a calculator, not.
1,000 difference in actual and approximation. Okay, and again, I know this seems a little silly right now, like, well, why wouldn't I just figure out cosine of 1.75? There's more coming with this.